Welcome to Innovation Insights for the month of May 2022. We've now done this for a year, and we've appreciated everybody that keeps signing up and coming back, and those of you for whom this may be your first event. Next slide, Kim. So just a quick reminder, the IACMI vision and mission statement. Our vision is to improve everyday lives through the power of composites. Our mission is to convene, connect, and catalyze the composites community to accelerate advanced composites design, manufacturing, technical, and workforce solutions to enable a cleaner and more sustainable, more secure, and more competitive U.S. economy. We revolve around these three themes of convene, connect, and catalyze, and in that order. Next. Around those, a lot of opportunities to engage with IACMI and with others in the industry, through projects, funding, interns, facilities, consulting, education opportunities, and so forth. Next. Just a reminder, everybody, and our third speaker, Mark Morrison, today will be talking more in depth about this, but our summer members meeting comes up next month in Salt Lake City. We expect a pretty robust program. It's already come together, and Mark will go into that. Great reception. Great opportunity to network with everybody in a very beautiful part of the country. So it's the first time we've gone west to Mississippi for well, no, it's not. It's first time we've gone west to Denver for a meeting anyway. And we expect it to be a good one. Next. Just a reminder about Innovation Insights. It is this is recorded, and once it's edited and we take out the technical glitches, this one will be posted as well on our website. So everyone since the beginning one last May is up. So if you missed something, you can always go back and capture it again. Next to Kim. Just a little bit about where we're going from here. We hit the midway point. We will not have Innovation Insights next month because we will have the members meeting in Salt Lake at the end of the month. But here are the dates through the rest of the year for that. They'll all be on Mondays at noon, unless something gets in the way to force a rescheduling of that, but typically around the middle of the month. And let's go to the next one, Kim. So today's, we're going to get started right away. We have three great talks today. First off, we'll start with Dave Singer and Joel Kline of Carver Wabash MPI to discuss presses. And I think you'll find that they make presses that you may not realize they do. I mean, a lot of people have seen the laboratory presses, but you'll see that they've gone up in size with a lot of new features. That will be followed by Dr. Paul Kladitis from the University of Dayton Research Institute, and then Mark Morrison, who is IACMI's Director of Communications, will give everybody a sneak preview of that upcoming members meeting. So I'm going to start right now by turning it over to Dave Singer and Joel Kline. And gentlemen, you can start your presentation.
Okay, thank you, Dale, for inviting us in and participating in this event. I'm Dave Singer, Sales and Marketing Manager at Wabash MPI Carver. Been here for a number of years in different roles. Today, Joel Kline, Regional Sales Manager, is participating as well. So we look forward to presenting. Now, I'm going to need a little help to make sure I can get this presentation up on the screen. Do I just share my presentation and can you see that?
I'm not seeing it yet. If you go ahead and
go to
share screen.
Okay.
Yeah, the green button to share screen.
All right.
It should be at the bottom. Out there.
Minimize that again. Share screen. There we go. So now I can.
And then you'll need to click on the presentation.
Now.
Can you see it now?
Not yet.
Okay.
If you're having trouble with it, I can always run it from here too.
Okay, if you don't mind, because I cannot get it to come up here.
Let me make sure I'm opening the right one. And yep, it's just one of those technical glitch days, but we are working through it. So let me try to share mine again.
There we go.
Just put it in the presentation mode and we're speaking.
Yep. All right, we
There you
should
go.
be ready to
Okay,
go.
all right, thank you.
Perfect, thank you. Okay, yeah, if you want to go ahead to the next slide, that'll be fine then. Okay, just a little bit about our company. Wabash is in Wabash, Indiana. Oops, is it? There we go. Wabash, Indiana, founded in 1941. We built like Dale said, we built a myriad of different equipment here, 80 employees. Try to do everything in-house that we can as far as manufacturing, all of our engineering. We utilize the latest in design to make sure that we're building our frames and platens properly for the application. We can service what we sell and have for a number of years, and we are ISO registered. Okay, next. So core markets for this company, obviously composites is a huge part of our application base in many different areas, a lot of aerospace, recreational. We do some rubber molding, plastics, a lot of thermoset too, which with EV coming on, motor stators, that kind of thing. And then just a myriad of different custom applications that we do as well. We also have a product line, Carver press. Carver is a laboratory style press. As Dale said, a lot of different applications, fluid extraction, briquetting, proppant crush testing, X-ray and XRF spectroscopy, analysis pellets, just a myriad of different things in that realm. Okay, next. Real quick on our product lines on the Wabash side, we have a baseline platform of, is that advancing on its own? I'm sorry if it is. I thought I turned that function off there.
I don't think so. I think it's just one of those days. I'll keep a better eye on it. I'm sorry about that.
That's okay. We have two compression press lines, Genesis and Vantage. The Genesis line goes up to about 150 tons. And then next slide, I'll try to speed this up a little bit too, so we get through to the applications a little bit. The Vantage line goes up through 1,000 tons, and we build all kinds of different configurations. The transfer, go ahead to the next slide. The transfer molding applications, and we do get into some composites with these presses as well. Vacuum presses, again, just another part of our product line. All these can be done in both applications for heated, cooled, all kinds of different clamp forces and sizes, and an array of accessories. Okay, next slide. The Carver line, relatively simple hand-operated presses for some basic applications, a lot of R&D, a lot of plastics testing, rubber testing, composites testing, making plaques, that kind of thing goes along with these presses.
Mostly benchtop models.
Benchtop primarily, yes. Okay, next slide. And then probably our best seller in the Carver line is an Auto Series benchtop press. It's a kind of a lab strength press as compared to a Wabash freestanding press, but these are made for laboratory applications, a little less cost, but do have some very robust features for programming of heating, cooling, those kind of things. Okay, next. We also have a line of pneumatic compression presses, and we see a lot of these low force applications in a lot of composites labs for just some low force molding applications. And we can get down into the hundreds of pounds up to 15, 16 tons range on these types of machines, using some load cells and some feedback loops. Okay, next slide. So I'm gonna let Joel talk a little bit. We're just gonna get right into where our presses fit in the composites molding applications market. So we've got a few slides on that, and I'll let Joel take over for a bit.
Yeah, we wanted to talk a little bit about the applications that our different presses are used for, whether they're small laboratory presses or large laboratory presses, or even production machines. So the first most basic type of molding that we do is thermoset molding. And if you let us know what clamp force you require and the cavity size, then we can usually customize a press or come up with a press from our standard line that would fit your needs. But the key thing with our thermosets is heated platens. They're either heated platens or heated molds that are generally used. As far as the way we heat our platens, we have 3 ways. We have electric cartridge heaters, and the temperature range for those is, our standard is 500 degrees Fahrenheit. We also have 650 degrees Fahrenheit and 800 degrees Fahrenheit. We also heat with, as a heating medium, oil. If you want hot oil, we can heat up to 500 degrees Fahrenheit with that, or use steam, which we can heat up to 450 degrees. So all these thermoset machines are heat only, and a typical cycle looks like what we've got listed there. Preheating of the platen or mold, inserting the thermoset material, whether it's bulk molding compound, sheet molding compound, some type of epoxy. Those are loaded into the mold. Press is closed for a desired time, and then it dwells there until the cure time is timed out. The press opens, and the parts are removed either by hand or by an ejection system. So typical parameters we need to look at on those machines is clamp force, the temperature, and the dwell time. In addition, we have things called bump or breathe cycle, or maybe you've heard it called degas cycle. Those are used a lot of times in composite materials. Also pressing speed, that's how fast the press closes at the clamping force. So those are some of the different things we look at for the thermoset applications. Next slide, please. So in addition to thermoset compression molding, we also do thermoset transfer molding. So in this case, we have a transfer cylinder that's mounted on the top of the press. And then we can add material into the transfer pot and inject that material into the closed mold. So again, similar to the layout on the thermoset compression, with the addition of the transfer cylinder on the top.
One thing that's very common in these type of applications is to have some sort of a knockout system. So when the press comes open, the parts can be knocked out of the mold automatically as part of the cycle. We can also profile the transfer cylinder in case you want to control more closely how that material gets shot into the mold cavity itself. So those are just a few of the options that we offer on these.
And on the transfer presses, some of the typical parts they'd run on those. We're seeing a lot of like EV stator production on these. We're seeing different kind of coils, different cables, where there would be a ground power cable, or maybe it's a larger cable for a submarine or some type of application like that. So something where the part needs to be encapsulated around, or the leads need to be encapsulated around.
And what makes it transfer appealing is, say, over an injection machine is, you're filling this material with fiber, different lengths of fiber. Now you can use the transfer to inject that material instead of having to go through a screw or anything like that. And these normally are in preforms of some nature that are dropped into the transfer cylinder after the clamp is shut and at temperature. Anything else to add on this one, Joel?
I don't think so. Let's go to the next slide. So as opposed to our thermoset materials for our thermoset compression molding machine or our thermoset transfer machine, these are thermoplastic compression molding machines. And we see this a lot more lately, but they require, instead of just heating, they require heating and cooling of the material. Again, if you let us know what transfer for, or what clamp force and what platen size that you need, we can design a press around that application. But typically the typical cycle for the thermoplastic compound is it's loaded into an unheated press or unheated mold as opposed to a heated mold. The press is closed for a desired force, and then the platens are heated up, and usually it's a ramped heating. So it's a ramped heating rate. The press dwells under that heat rate, and maybe it's several ramps of the heat during that recipe. Then the presses are cooled, and again, those can be cooled down, can be crash cooled, or they can be cooled at a controlled rate. After that, the press opens and the parts are removed again by hand or in an automated fashion. A lot of times on these, we're seeing all kinds of different shuttle systems, things like that, to get the material in and get the material out of the mold cavity itself. If you go to the next slide, this gives you some different approaches that we've seen to thermoplastic compression molding. So some are just like the heating and cooling in the mold, as we looked at on the last slide, but some have two clamps, one heated clamp and one cooled clamp, with the compound or mold transferred to the heat, from the heated press to the cold press. And that can be either manually or in an automated fashion. I think that's, people are looking for the faster cycle times, less energy usage because you don't have to heat up. In this case, you don't have to heat up and cool down the platens. You can just slide from a heated press into a cooled press and close down on that. The one caveat to that is it does require the pressure to be released between heating and cooling. Some products can handle that and some cannot. So that's something that needs to be looked at for that type of application for thermoplastics. And then the third one, I'll let Dave talk a little bit more about that one as far as transferring the material in and out.
Yeah, we're starting to, and I'm sure a lot of those listening in have seen a lot of the applications where you're trying to heat the material outside of the press, transfer the material into the press heated, and then you're temperature controlling the mold or the platens to cool down that material so it can be handled and set. And the lower picture there on this slide is actually our press at Purdue University. And I know Dr. Pipes and his team there and Jonathan Goodsell have worked extremely hard in coming up with different variations of how to do that effectively. And they're using our press for that. But we do see that as an emerging market. And it seems like the variables to that are how to hold this material, how to get it underneath the IR heater, how to hold it tight so you can heat it and then transfer it into the mold in a very quick fashion so it can be clamped up and formed. And we have several customers of ours that have taken our machines and done their own thing with that kind of IR heating system. So we are looking at what can be developed more on a mainstream nature, but by virtue of the fact that all materials are different, there's different fill, there's different polymer, there's just so many variables that those of you who are in the molding or in the materials side of the business know that very well, better than we do. It's just a tough thing to overcome. So, we're always looking for ideas ourselves. If anybody has any good ideas that would be good for a mainstream application for that, we're always willing to listen to those as well. So I think that's all on this slide. Joel, is there anything else you wanted to add?
I don't think so. I think that gives a kind of a pretty good overview of the different kind of thermoplastics molding that we're seeing. But it definitely is a big part in a growing market that we're seeing right now.
Yeah. Okay, next. And that's really all we had. We're trying to stay on task here with the time. So I'm going to say thank you and throw it back to Dale.
All right. Thanks, Dave. Thanks, Joel. I'm going to ask one quick question while Paul Kladitis, who's the group leader for multifunctional structures and materials at UDRI, loads up his presentation. But just one quick question is, have you guys seen issues with getting, what are your lead times like now? And are you able to fulfill orders, and it's still in a timely fashion?
We've much like everybody else in the machining industry, the press building and equipment in general, we are struggling a little bit to try to fulfill some orders based on availability of parts. We're all know about the chip shortage and we're falling into that as well. We're having trouble with specific PLCs, different electronic components that go into our machine. And unfortunately, it just takes one part to hold up a major shipment. So we're working through those right now.
Okay.
In general, I'd like to say it's gotten better, but I think we're just kind of at a status quo where we have to deal with it until the supply chain gets in better shape.
Okay.
I heard that at JEC as well from a lot of different customers and vendors I talked to about the shortages they're facing. So it sounds like it's the same pretty much worldwide.
Yeah, so I just encourage people to get your orders in early.
We do. That's
Okay.
part of
So
our.
if any of you have additional questions for Dave or Joel, put them in the chat, and you guys monitor that chat. And you can answer them as the rest of the hour goes along. So I'm going to switch over to Paul again. Paul is the leader of multifunctional structures and materials for University of Dayton Research Institute, and I asked him to come on and talk about carbon nanotubes, and partly to say, I think the hype years of carbon nanotubes may be behind us, and we're actually into the commercialization phase. So, Paul, why don't you show us why that's the case?
Sure. Good afternoon, everybody. Kim, do you see my presentation in presentation mode? Is it looking good?
It is. You are the winner of the sweepstakes today. It's working. Thank you.
Okay. All right. Thanks, Dale, for introducing me and inviting me to give this talk. Again, my name is Paul Kladitis. I'm the leader for the Multifunctional Structures and Materials group at the University of Dayton Research Institute, or UDRI. UDRI has several groups, is divided into several groups. My group is responsible for materials, polymers, structures, composites, and nanomaterials research and development. And I was asked to give a talk and give a little insight onto what carbon nanotube technologies that we are commercializing and making attempts to commercializing or are commercializing. So this is just a little peek under the hood of what we're doing. It's not comprehensive of the whole country or the world by any means. And there's more I could even say, but I won't be able to fit it all in. So feel free to ask me questions when it's over if you're curious about something else. And so let me begin. So Kim, is this going to be recorded? So if people want to go back and watch it, they can see this like contact information and stuff, or?
Yes, it will be recorded and we'll get it posted on the IACMI website probably within a few days.
All right. Cool. So I can speed along then. All right. So what I'm going to talk to you about today is I'm going to give a quick introduction where I'm going to talk about nanotechnology in general. You have to talk about nanotechnology when you're talking about the carbon nanotube. And then I'll talk about the carbon nanotube, and then I'll give those examples of what UDRI is doing to commercialize carbon nanotube technologies. And we do it in two ways. So we help commercialization of CNT-based products by manufacturing and productization. By manufacturing, what I mean is we know how to make them. We know how to make the carbon nanotubes, and we know how to make them cheap and at an industrial scale. And that helps the commercialization of the technology, because you're not depending on hype or other companies selling carbon nanotubes more expensive than gold, and completely short-circuiting potential for different products. So we understand how to make them, and that's really helpful. And then, like a lot of people, we figure out how to use them in products, how to enhance products. I'll talk about that, and then I'll conclude. All right, so nanotechnology. There's two definitions that are similar, major definitions. The US has an official definition, and it's nanotechnology is the understanding and control of matter at dimensions between approximately 1 and 100 nanometers, where unique phenomena enable novel applications. It can also mean science, engineering, and technology that involves imaging, measuring, modeling, and manipulating matter at this length scale. So it doesn't have to do with just materials. And this comes from the, this definition comes from the National Science and Technology Council Committee, which I'll talk about in a second here on the next slide. And then Europe had its own definition. And they said nanotechnology is the study of phenomenon and fine tuning of materials at atomic, molecular, and macromolecular scales where properties differ significantly from those at a larger scale. And another part to their definition is nanomaterial means a natural, incidental, or manufactured material containing particles in that size. And a funny story about this, so this is the European Union's definition of nanotechnology and nanomaterials that they put out in 2011. So at the same time they were defining nanomaterials, they were also, because of hype, because of negative hype, they were putting bans on nanomaterials. And when they combined their bans, their proposed bans, and this definition, it turned out that milk, ice cream, and yogurt were going to be banned. And people went nuts because of the molecular size of the proteins in milk. And so I'm pretty sure they backed off on both of these things, the definition and the bans. But anyway, that was funny to me. Okay. A little bit about nanotechnology in the United States. I don't know if you know this, but we have a national nanotechnology initiative. To date, $38 billion has been invested in it. So to this year actually. It was first proposed at the President's Office of Science and Technology Policy in March 1999 by Mike Rocco, who is the senior advisor for nanotechnology at the NSF. He's still around actually. And then it was formally established in 2001, I believe, by Bill Clinton. Okay, so its purpose is to keep the US on top. They knew that nanotechnology would be a cutting edge field that would lead to insights across technology. So they were thinking, we got to be on top of this in the whole world. So they stood this up. The national, here's the budget right here, starting in 2001. So basically up to today, it's about $2 billion each year gets invested in it. And what that $2 billion is every government agency has to devote some portion of its R&D to nanotechnology, and that's why I gave you the definition of nanotechnology, to technology that fits the nanotechnology definition. And they add that all up, and that's where that budget comes from. Where's the abbreviation for the nanotechnology initiative is NNI. Where is the NNI run? I used to be on this committee. So it starts in the President's Office of Science and Technology Policy. Then under that is the National Science and Technology Council. Then that council has a committee on technology. And then that committee on technology has a subcommittee called Nanoscale Science, Engineering, and Technology, or NSET. And that's who actually runs and executes the NNI and tracks everything and leads the initiatives. And I have, you can look it up and you can read their budget supplement for FY22 here, which is where I got the latest data. I used to help make that document. Okay, so what did we get for this $38 billion? Well, one of the poster children for nanotechnology is the carbon nanotube. There's a lot of other nanomaterials, a lot of other different nanotechnology out there in nanotechnology, in medicine especially, and stuff like that, that is not carbon nanotubes. But I would say carbon nanotubes is the most infamous star of nanotechnology for good and bad reasons, or hype reasons. So here's how the hype works. So here I have a picture of a exceptionally long single wall carbon nanotube that might be 1 nanometer in diameter, and if it was 1 millimeter long, that would be 1,000,000 nanometers, and that would, if you tried to look at this in an electron microscope, it would be a task similar to following a piece of spaghetti laying on the ground that's a mile long from an airplane. So you could zoom in with a telescope and maybe see the spaghetti laying on the ground, but then if you wanted to see the big picture of it, when you zoom out, you can't see it. But that's some of the interesting things when you're dealing with nanomaterials with these high aspect ratios. But anyways, what's the big deal about carbon nanotubes? Well, academia told us right away, it's 214 times stronger than steel. Its elasticity is 5 times steel. It has, so the standard for electrical conductivity in our day and age is copper. It has 5 times higher electrical conductivity than copper. It can carry 1,000 times more amps per area than copper. The thermal conductivity is 15 times better than copper along the axis, or 3 times better than diamond along the axis. But this way it's pretty low. So that means you have this amazing material that can conduct heat incredibly in one direction, in the other direction you can flip it around so it doesn't conduct heat very well. Amazing. And all that in a material that's half the weight of aluminum, half the density of aluminum. Amazing. And Richard Smalley, who won the Nobel Prize for the discovery of fullerenes, which is the same crystal allotrope as carbon nanotubes and graphene and stuff like that, from Rice University, which I'll be mentioning in a little bit. He said it's the strongest fiber that will ever be made. What can, how can you go wrong with this? Well, what people didn't understand, or what people didn't know, is that, so that's for the individual carbon nanotube. When you put a lot of carbon nanotubes back together, so you can make a big object like the door panel of a car or something, something big that you can hold, you lose these properties. These properties kind of go away to some extent in the wash when you bulk it all together. And so that's where the hype came from. People were selling this, but then they weren't seeing this. Well, and they also couldn't make much of it. And the cost of it was just to get a thimbleful was more than gold per ounce at the time, a long time ago. But today we can make them very cheap. And we can make them in industrial scales. And we know how to actually take some of these qualities and translate them into the larger world. So let's talk about that. So here's some examples after the hype settled. Oh, and by the way, if you want to read a good history of nanotechnology in general and the hype, I don't know if you can see my thumbnail, but this is a good book. It's called Nano Hype, written by David Berube. It's a good book. I've had it for several years, and so you can get that. But anyway, so after all the hype had settled about carbon nanotubes, there were some strong players that found real benefit from their products, came along. And here's just some of the big names. Not everybody. This is not everybody, so I apologize if I'm leaving someone out. And this is not all the different kinds of carbon nanomaterials that we could talk about. There's others. So one is Nanocomp, which was purchased by DuPont and then eventually by Huntsman. And they make these gigantic, at industrial scales, all carbon nanotube sheets. So the carbon nanotubes, it's all carbon nanotube in that sheet. It's not held together with polymer or anything. And they also can make threads and yarn. And then actually University of Dayton Research Institute was a pioneer in making nanomaterial-based, carbon nanotube-based improvements. And right here is a scanning electron micrograph of a single carbon fiber with carbon nanotubes growing off of it. And what we do at UDRI is we can take whole 60-inch wide rolls of carbon fiber cloth, send them through a reactor we have, and grow these carbon nanotubes on all the carbon fibers throughout the cloth. And then we can use that to lay up composites and increase electrical and some mechanical properties. And then we also, because of our expertise in growing, we were able to help another company called N12 initially, and then they eventually were bought by NAWA Technologies in France, and NAWA has established a NAWA America, is vertically aligned CNTs. So we use our same reactor that we used to grow carbon nanotubes on carbon fiber cloth. We take in a bare substrates and we grow these vertically aligned carbon nanotubes. And if we, this is the substrate they're growing on here, and these are the vertically aligned carbon nanotubes. It looks like a rug, a really nice rug, but this is at the nanoscale. We're talking about the height of this. So if you zoom in, you can see the individual carbon nanotubes here, and here's the top. The bottom is right around here. It's not viewing this close up, but anyway, the height of this carbon nanotube carpet or forest is about, I'm not going to tell you exactly because that's proprietary. That's what makes the product work. Is about, let's see, human red blood cell. One of your human red blood cells is about 7 micrometers, or in slang microns in diameter. So this height is about 3 of your red blood cells stacked up end to end. And we have to control that height very precisely. And these carbon nanotubes are used for putting in between layers of composites and strengthening the composites. And I'll show you that in a second. They're also, and in France,
we've got about 5 more minutes.
Okay, and in France, they use them for supercapacitors. And then a new person coming along is a spinoff from Rice University, where Rick Smalley came from. And similar things to Huntsman, carbon nanotube sheets, and yarn. Well, anyways, the carbon nanotube based products, they're strong, lightweight, flexible, conductive, corrosion resistant. Multifunctional means you can give them other properties. They're biocompatible, and it's an alternative to metal or polymers. So here at UDRI, here's one of our industrial production lines where we grow the carbon nanotube substrates. You can see them coming out on the conveyor belt. We can do about 30,000 square meters annually, and that's not even, that's just the basic technology that we have. We could increase that if we wanted to. We are the production for NAWA for the composite-based application. So another thing that we're doing to help commercialize the CNT products is with our tailored fiber placement technology. It's like a big sewing machine where we can lay down carbon fiber toe or make preforms. And here's some examples of preforms around the screen here. This is how it works. There's a needle that with thread, you can stitch the carbon toe down and make all kinds of 3-dimensional shapes. But we found that we could use the carbon nanotube thread, and the carbon nanotube thread is very unique. It is the only thread. So on this slide, it's the only thread that exists that's already in a robust carbon state. That means it won't melt. It can withstand high temperatures up to like carbons. Plus it's stitchable in conventional equipment, and it has multifunctional properties. So all those properties I showed on the other slide. And however, it requires a special sizing to stitch with it because the CNTs have a high coefficient of friction and get with things they rub on. And to get that to work, we had to figure out the proper sizing to make it sewable. And so we have a patent on that. All right, and so here's some examples. Here's what a stitch looks like in a composite. So these are the 2 ways in manufacturing we're helping to commercialize carbon nanotube products. Now in productization, so when our IACMI Demo 6 report comes out, I don't think it's out on the website, but you can read in detail what we've done, for example, in the area of eVTOL aircraft. So this is some examples that we'll talk about in our Demo 6 report, where we saw our target places for using carbon nanotube products. You can read more about that in our IACMI Demo 6 report that should be out soon. And I'll talk about some more specifics. So I can't talk about some of the specific products, but I'll tell you the areas that we're doing it in for customers. A lot of it is proprietary. So we use the carbon nanotube based technologies to make stronger composites. And here's an example of the vertically aligned CNTs placed in between 2 plies of carbon fiber. There's a nice close-up shot. These are the carbon fibers coming out at you, probably about less than 10 micron diameter fibers. But this increases many mechanical properties of the composite by putting the vertically aligned CNTs in there, or it's called NAWA stitch. Here's an example of making a spacecraft hull where the ribs are stitched down using TFP and the CNT thread stitching. Santa Cruz Bicycles out of California, they started using NAWA stitch to make their composite rims, and they are the world champs. And one of the reasons they're the world champs is because their rims don't break when they're in their competition. So you can see all about that in the news that has the NAWA stitch. So this is real. We also use them in composites to embed electrical functionality like heating. Here's an example of making embedded heaters for de-icing in composites. You don't need separate boots anymore. The composite itself can be a good uniform heater. Also for RF management, EMI shielding, power storage. They're enabling us to have power storage in composites, and that's something that's really newer for us. And wires and cables. Here's some examples of wires and cables that, except for the connector, the rest of the wire and cable is all CNT. So you're seeing nothing but carbon nanotubes. And Minnesota Wire and Cable has, using the NanoComp product, has been a pioneer in that I've been working with for a long time, that I've helped them to commercialize that. I just came back from France about a week ago, and NAWA is using the vertically aligned CNTs in France to make super or ultra capacitor. An ultra capacitor is a fast charging and high power supercapacitor. And for battery electrodes, here's one of their supercapacitors, and they have the NAWA Racer, which you can see all about it on YouTube. It's real. I was on it. That's in their office. So this picture is just about a week and a half old right there. And then finally, so the carbon nanotubes, they're not the cheapest thing in the world. And if they were cheaper, people would be using them in more applications actually, but that's about to happen actually. So if this new concept that our country is going down, where we take methane and use it to make carbon nanotubes, and a byproduct is hydrogen, there's several big oil companies wanting to scale this up, and you can see all about it in this too. But if that happens, this stuff's going to become dirt cheap, and we're already involved with people making, we're planning on making building materials with the carbon nanotubes to build houses and buildings out of. So civil engineering is going to be getting involved with this, and they have been dabbling in it in the past, but this is going to be a game changer when it becomes dirt cheap. And I have some of the people that we're working with in this area, Mark Goldthorpe, these are his designs, and the Carbon Hub, that's what they're all about. So if you want to go check out the Carbon Hub, they're about this concept. All right, and so in conclusion, nanohype has long settled, and some serious CNT producers have emerged with products with real benefit. CNT costs are very affordable for the current higher end uses, but in the near future, the costs have a significant chance to become cheap as dirt to be used as commercial and residential building materials. And we have been helping commercialize CNTs for many years, especially under Brian Rice, and enhance composite structures and products in both areas of manufacturing and productization. So that's it. Any questions? I guess.
Yeah, I'll ask if anybody wants to ask questions to put those in the chat, and Paul, take a look at that and see if some come across. But clearly, we've entered a new era. You know, I was the one that became very skeptical of nanotechnology,
and rightly so.
Yeah, and whether it had real commercial opportunity, you know, but I've become a convert, and it's good to see some positive things happening there. So thank you again, Paul. So we'll go to our final speaker, which is Mark Morrison. Mark is going to run us through it's a preview of our summer members meeting, which is starting in just over a month. So he'll remind you how to sign up for that. So Mark, take it away. Mark, you're muted.
Try that again.
You got it now.
All right. Thanks, Dale. Thanks, everybody. And appreciate your time. What we wanted to do today as we end our Innovation Insights is just kind of give you a little bit of more insight into what's going on with the summer members meeting coming up June 28th, 30th. Hopefully this is not news to you that we're having a summer members meeting and the dates. I hope many of you on this meeting are registered. If not, by shortly after this, that you will. So we are going to be in Salt Lake City. You see the dates, the 28th through the 30th. And we're presenting this in partnership with UAMMI. Many of you know UAMMI. Obviously, Utah has a rich composites heritage. And Utah is a very important state for IACMI, certainly our members. You see some of those here on the screen as they and as we work together to foster growth of the composites manufacturing industry, certainly in Utah. And then in addition, to defense and aerospace and aviation, Utah is a leader in innovative programs for recycling of composites and carbon fiber. So it's naturally that we want to be there in Utah and looking forward to it. It's interesting because a couple of you've already talked about being at previous events, JEC and others. We are going places to kind of steal a phrase from Jeff Sloan at Composites World. We're on the road again and we're networking in person again. So you're going to see a great opportunity coming up here with our members meeting. Dale, you heard Dale mention Convene, Connect, Catalyze. That's the way that we kind of bring to life the mission that we have. And so these are some pictures from last year, kind of seeing that in action where we bring people together and you're able to convene and connect and then later catalyze and make real things happen. So what's going on? What's the agenda like? So this is just a very, very high level agenda. I'm going to show a more detailed one here in a second. But we have working group meetings on Tuesday. And I guess I could minimize my screen would be helpful if you're seeing what I'm seeing. We've got working groups on Tuesday and Thursday, the 28th and 30th, and then the main programs with speakers and presentations and a networking reception on Wednesday, the 29th. We will be meeting at the Sheraton Salt Lake City right downtown, very convenient. You can walk to several restaurants. It's easy to get in and out of, plenty of parking too if you're local and going to be arriving. We're really excited about a networking reception that we have at the Natural History Museum of Utah. You can kind of see the photos for yourself. It's a spectacular venue and the views are really unbelievable. So if you've been to Utah, you know that. If you've been to Salt Lake City, I'm not telling you anything new, but if you've not, you're really in for a treat. And what is neat about this venue, it's going to allow us to have a really neat networking opportunities, both outside and inside. So we're looking forward to kind of showing this off, and we're glad that we're going to be able to have our networking reception at the venue. We do have an impressive lineup of speakers, presenters, and panels. Many of those we've announced, others will be announcing more soon. You can kind of see those on the screen. Again, if you follow IACMI with our news, you've seen us announce these. Again, we have, a top person from the Department of Defense. I won't go through all the themes because you can see what I've got on the screen, but we're very pleased to have Adele Ratcliffe with DOD, Jeff Sloan from Composites World, and Zach Valdez and Marcy. Zach is with NIST Manufacturing USA. He's really going to bring a neat aspect because as agencies today and as companies, as you apply for federal funding, you're very familiar with that there's some initiatives with this administration about disadvantaged communities. So Zach is well versed on that. He's going to be able to share some insight that I think will be beneficial to everyone in the room. And then Marcy, many of you may know Marcy, she's going to lead a very impactful Women in Composites panel. In addition to that lineup of speakers, you see many of the folks here that we have on the screen, several of our working leaders, several of our leaders at IACMI. But we are going to have working group reports. We're going to have a panel featuring small, medium enterprises of IACMI members. And then what's really neat too is our IACMI Innovation Core partners are going to share some collective capabilities. You've heard many already from Paul, because he and Brian are one of our core innovation partners at UDRI, and you can kind of see the work that they're doing. So we're going to be happy that these leaders will be able to share their capabilities. A reminder, working groups on Tuesday and Thursday. And then, sorry about the size of this, but we do have a lot going on Wednesday. All of this is available on our website. I'll share that link in a minute. And then if you go to our registration site, you'll see this too. But we do have a very robust agenda on Wednesday. We're trying to make this very efficient where you can fly in and fly out on Tuesday and Thursday. And then I know we're kind of pressed for time, but wanted to kind of share that we do have, there are a number of benefits by meeting in person, and hopefully those are obvious to many of you that have been part of that. And then the other is I want to encourage you, if you've not already, please register today. You can do that at this link, and Kim has put that in the chat, or we'll be putting it in the chat. You can also visit our website, acme.org. With that, Dale, I'll turn it over to you.
Thanks, Mark. And somehow we managed to get back to getting all these in by 1 o'clock, and that way everybody can get on to the rest of their day. Again, this recording will be up in the next couple of days. If you have any questions or want us to connect you directly with any of the speakers, just let us know. Drop us a line at IACMI@iacmi.org, and Kim will be more than happy to connect you to any of our speakers if you weren't able to catch their contact information. We thank you for attending today, and we will see you hopefully at the members meeting. Thank you.